and it's along that boundary or the cold front where most of the active weather occurs. So now what I want to do is I want to pull up the latest surface analysis. Back out of here, and I'm going to go to this and share a different screen. So I'm going to share that. Okay. So this is the surface analysis from 4 o'clock this afternoon. Excuse me, 3 o'clock this afternoon. Forgot about the time change. All right, first things first, you got to be able to read a map. So we know we're looking at the map of the United States here. And you can tell that not all of the plotted METARs are on this map. You can't do it. It would just be too busy. But basically what it's doing is it's giving you the sense of what the surface, what the environment's like at the surface, okay? So the different symbols that you're looking at here, obviously you can see the plotted METARs in there, but you have these kind of brown or dark red lines. Those are called isobars, I-S-O-B-A-R-S, isobars. And an isobar is a line of constant pressure, all right? The pressure is the same all along that line. So we would take the pressure reading from the raw METAR, the plotted METAR, and be able to kind of connect the dots, I guess you could say. And we use that to create the surface pressure. All right, it's a surface pressure map. From the isobars and the way the isobars are drawn, then we can be able, it tells us where the warm fronts are located. It tells us where the cold fronts are located. The purple one that you see is up there is called an occluded front. I'm not going to go into that tonight. That's a little deeper than what I want to do. But again, it shows you where the warm fronts and the cold fronts are. It's all part of a low pressure system and gives you a sense of kind of, if you're in an area that's south of the warm front, you might see, the winds are going to do a certain thing. The cold front in the cold front, it might be drier behind the cold front. It's probably much drier behind the cold front, that kind of thing. But the one thing I wanted to point out today, because it's so perfect, is see how tightly packed the isobars are from the Great Lakes to the southwest down into Texas. See how tightly they're packed? The closer those isobars are together, the stronger the wind. So much like we're going to experience tomorrow, that weather pattern is going to dive down southeast and continue southeast tomorrow, and it's going to be windy here tomorrow. All right, you can see the plotted METARs up in Iowa and in Illinois and Michigan, how they've got sustained 25 knots of wind. All right, now I don't think we're going to get quite that windy here tomorrow, but we're definitely going to catch the front edge of that, and we are expecting windy conditions. Daniel asked, how far up in the atmosphere is considered the surface? Right at the surface. Everything that you're looking at here is based off of what's going on at the surface. All the automated surface observation stations that's taking the plotted METARs that you see there. It's all going on right at the surface. Let's see if there's anything else that I wanted to point out here for you. Okay, so let me go back to my presentation here. Okay, so our presentation today isn't just about what goes on at the surface. I love to talk about what's going on aloft as well. And the reason why I wanted to bring it up and why we're talking about the observations in 3 dimensions, when we talk about upper air patterns, is because a lot of people forget, and I did it, I was guilty of it when I first started doing meteorology, studying meteorology, was that weather's not just north and south and east and west, but it's up and down too. Got to take that into account because it's a large portion of being able to forecast. Okay, so in order to answer the question of why are some storm systems stronger than others, we quite often, when we're talking about upper air patterns, we talk about the synoptic weather pattern. And a synoptic weather pattern is usually on the scale of hundreds of miles. This map that we're looking at here is what's known as the 500 millibar chart. At 500 millibars in the atmosphere, you're usually looking at right around 20,000 feet. And this is normally the level that drives weather systems. It's why we look at this level so often when we're doing the forecast. So when we look at these maps, we're looking at the shapes and the positions of the troughs, right, and the ridges. So we're looking at the shape and the positions of these, right? The trough is associated with a low pressure system, and a ridge is associated with a high pressure system. Well, this is important because those upper level troughs and ridges are responsible for creating weather at the surface. So this is a good schematic because it shows the ideal location of where a well-developed surface low would be located in comparison to an upper level pattern. And that's what we're going to focus on here. So a couple things to notice. First, I want you to look at the direction of the air associated with the high pressure. That's the big blue H that you see there. And let me change my color here. Okay, so at the surface, all right, the lower portion of this, the winds are clockwise around the high pressure, counterclockwise around low pressure. Okay. And then in low pressure, you have air that can't go down into the ground, so eventually it's going to have to rise. So you have rising air in a low pressure system and sinking air in a high pressure system. And you can kind of see the cyclical aspect of this, right? Kind of all cycles here. Let's see. So the most important part of this sketch is the ideal position of where the well-developed surface flow would be in relationship to the upper level pattern. And we'll dive into that in just a second, but there is one more thing that I want to be able to point out to you. So here's what's known as a 500 millibar chart. And what I want to do is I want to take a look at the anatomy of the upper air low that you're looking at here. All right, the upper air low that you see is this trough that runs from Michigan down towards Texas. All right, it's this trough that you're looking at. Now, unlike a surface map, these solid lines that you're looking at here are not called isobars. They're not lines of constant pressure. What these lines are telling you on the 500 millibar chart or any other chart that you're looking at, 850 millibars, 700 millibars, at 500 millibars for this particular chart, these lines are telling you the height at which in the atmosphere at which 500 millibars is located. All right, so it's a little bit different than a surface map. So the way these are read is, here's just for an example. One of these lines in here is got this 555 designator next to it. You put a 0 at the end of it. And this is, well, if you leave just 555 alone, it's read as 555 decameters. But you put a 0 at the end of it, and it's 5,550 meters. All right. Meters is roughly 3 feet. So if you multiply that by 3 feet, that comes up to about, I think, 16,000, little over 16,500, somewhere in that range. And then this one here that's towards the center of the upper level low is 535 lower, okay? And this is actually, if you convert that, put a 0 at the end and multiply it by, divide it by 3, or no, sorry, multiply it by 3, you end up with about 16,000, okay? So 16,600 for one, 16,000 for another. And what I wanted to do was kind of give you a cross section. If we did a cross section through that upper low of what that 500 millibar is, what's going on at that 500 millibars. And you can kind of see that that upper low, as it moves across the country, is actually in the shape of a bowl. All right, so I'm going to go back to that previous map. And again, see where the 535 is towards the center of the low. All right, that means it's lower in the atmosphere than the 555. And then I'll go to, this is the cross section of that. And that upper low is kind of in the shape of a bowl. Well, why is this important? Well, not only are we looking at what the pressure is doing and how, or what's the height of 500 millibars in the atmosphere, but when you start to get that surface low, the other thing we got to pay attention to is what's the temperature doing. So for this example, outside of that upper level trough, it's actually minus 17 degrees. So we're looking at the red dotted lines, and those are isotherms, or lines of constant temperature. Oh, sorry. In the center of the low, it's minus 36, much colder in the center of the upper level trough. Well, what's that doing? Okay, so we'll go back to that schematic. And in the center of the low, where it's minus 36, you have much colder air that's dipping down closer to the surface. Now, granted, it's still 16,000 feet in the atmosphere. But the gist is that, and what if you take our upper air class, which I think is sometime in December, I want you to remember this. Remember what we were talking about here, because you're going to look at what the upper air, when we launch our balloon each day, and the balloon is sampling what's going on in the atmosphere. It is the difference between what's going on at the surface temperature-wise and what's going on aloft temperature-wise that gives us our instability reading. So if you've got that really cold air that's diving down from higher in the atmosphere, it's diving down, and it's really warm at the surface, it's that difference between what's going on at the surface and what's going on aloft that gives us our instability in the atmosphere. Okay? Any questions as far as that goes? I know that's kind of a deep go here, and you'll have to excuse my crude drawings. I just made this up yesterday because it was something I wanted to try to explain. And in my previous classes, I've always tried to verbalize what it looks like as far as an upper low looking like a bowl moving across the country. But hopefully this illustrates it a little bit better. All right, so the second part that I want to pick on. All right, so before I go any further, Sean asked, what does geopotential mean? And it's just the height at which that pressure surface is. And we were talking about one's at 16,000 feet, one's at 16,600 feet. Geopotential is just the height at which that particular level, and that one we were looking at was 500 millibars. All more crazy meteorological terminology. And they're geopotential heights, and that's all that's telling you, versus the isobars that we talked about on the surface map. Okay, so the bigger part that I want to point out here is the position or tilt of the trough axis. You heard me say that earlier. So the position or the tilt of the axis tells us a lot what we can expect the reflection of the weather to be at the surface. So this position that we're seeing here is what's known as a positively tilted trough axis. Now I superimposed this black dotted line on here because I wanted you to see where the axis of the trough is. So if we put on our 3D glasses, when a trough is positively tilted as it moves across a landscape, it's more than likely going to create a surface flow, but one that's not very intense. Here's the, sorry, got ahead of myself there. So here's the surface low that's associated with that positively tilted trough. All right, and we've looked at surface analysis here, but we can look to see the lines of constant pressure at around this low is 1,012 millibars. That's not a very, very deep low, right? Also, I want you to notice that with that, where the axis of the trough was from the Great Lakes down into Texas, it's not very well located, co-located with the upper part of the system too. It's way out ahead of that upper trough. Here's an example of what's known as a neutrally tilted trough axis. All right, that axis runs north to south. And here's, I don't know why it's doing that. Okay, here's the associated surface low with that. And this low is actually lined up much better with the upper trough, and we can see that its surface low reflection is actually down to 1,004 millibars. That previous one was 1,012, so it's lower, stronger. It's more, slightly more intense low pressure system. But you can see a well-defined warm front that started to develop. Remember the red line in the surface analysis. You've got the cold front that stretches back into Texas, but you can see the green numbers on the surface, the plotted METAR. Those green numbers are your dew points. And as we start getting into the 60s, now we're starting to get into a nice, warm, moist air mass. All right, so we talked about a positively tilted trough axis, a neutrally tilted trough axis. Now we're talking about negatively tilted. Excuse me. Negatively tilted trough axis is more than likely going to give us some very active weather. Now, that can be severe weather or winter weather. It doesn't matter. But when a trough goes negative, the reflected surface flow has already, or it's going to deepen. And if you haven't noticed already by the dates that are on these maps, this is actually the upper level. You saw the upper level pattern. This is the surface low from December of 2015 when we ended up with 4 tornadoes here in Middle Tennessee in the evening. I think at least one of them was an EF3. And yeah, so here's the, from our website, this is the layout of the tornadoes that we had here in Middle Tennessee. Now, one thing that you got a picture here is, while we've been talking about things in 3D, everything's really in 4 dimensions. You got to throw time in as well. Now, I didn't want to go too deep into that, but what I want you to take away from what I just said is that the upper troughs can stay positive and move positive all the way across the country. They can start positive and become neutrally tilted, right? To get you that, so in time they become neutrally tilted. Sometimes an upper level trough won't get to neutral. It'll stay positive all the way across. Sometimes it'll go positive, neutral, and then get to negative. And this is an example of that. So this is from January of 2013. In the evening, the upper air, this is the 500 these two are the 500 millibar charts. They're 12 hours apart. All right, so you can see kind of a positive tilt at 7 p.m. in the evening to a negative tilt 12 hours later, slightly negative tilt 12 hours later. And what ends up happening when you swing from positive to neutral to negative, you end up getting a lot of spin in the atmosphere. Your surface low is getting more intense, which means you've got more wind doing at different levels in the atmosphere that are doing more things. If you took the severe weather, the severe thunderstorm class from a couple of weeks ago, Brittany talked about how wind shear plays into severe thunderstorm development. All of this stuff works in tandem together, all right? But all I want you to take away from this is that the atmosphere is fluid, and it's not just 3D, but it's 4D. You have to throw time, 4 dimensions. You got to throw time in as well. But for the big thing I want you to take away here is the idea that when upper level patterns swing like this, then we can get more intense weather. This is the surface low that went along with that. In the middle of this surface low, I'm trying to pick out a number here. So I see 1,008, 1,004, 1,002. We're probably around 998, maybe 996 with this surface low, which is a pretty intense surface low. But you can see how dew points have gotten into the 60s here in Middle Tennessee. Winds are out of the south, maybe even a little bit of a southeasterly component at Huntsville there you can see. But this particular day ended up giving us 24 tornadoes across Middle Tennessee. So Bill asked, did the trough go negative when the Nashville tornadoes occurred this year? Bill, I haven't gone back and looked at it. I need to go back and look at that, and I haven't, so I can't answer that question. I would assume so, just because of the amount of spin that was in the atmosphere. That's what ended up happening. All right, I got a couple more poll questions for you. This one jumps back a little bit, so let's see how everybody does. All right, that's just about everybody, and we'll share the results, and very good, fantastic. Long line on a wind barb equals 10 knots, and the short line equals 5 knots. Actually got a couple more here. Let's try this one. Troughs are associated with high pressure, low pressure, or pigs. Well, we're talking about weather here, so you can kind of throw out the third one, right? All right, that's everybody. And yeah, so troughs are associated with low pressure systems. Remember, high pressure is a ridge. And one more. Choose the answer that is most fitting. All right, that's just about everybody. So let's share the results. Very good. Fantastic. All right, warm front pulls warm, moist air into a region. What can be thought of as a dome of cold air? Well, cold front. I should say dome of air. And then most of the active weather actually occurs along the cold front as well. Very good. All right, so I ran just a little bit long, but I wanted to tell you guys before you go. Don't jump off here. I got a couple of requests of you. First off, these are the upcoming classes that we have left for Weather 101. I hope that you guys will join all of these classes because I've got some fantastic ones, and the presenters in these are really good. And then these two new classes that we got. So the class on damage surveys is going to be done by Matt Reagan. If you've taken his advanced spotter class before, he's doing a class in Weather 101 about how we go about doing damage surveys. And then we actually have an IMET, which is an incident meteorologist. And they go out and they're the ones that are responsible for on-site forecasting during forest fires. And so not everybody is an IMET in the Weather Service. There's, I think, a couple hundred. And they get deployed out there and they're the ones on the front line doing spot forecasts for the guys that are fighting the fires. So I actually have an IMET from the Tucson office that is going to be talking about fire weather and his experiences during all of he was out in California during the fires in California. So that'll be something to look forward to in his fire weather class. And then the upper air class that I referred to a couple times tonight in the middle of December. Make sure you grab that one too. And remember what we were talking about when it comes to that upper air pattern and that cold air dipping down lower. Keep that in mind. Okay, so my ask of you is that if you're not alone, if you would, this is my email. If you're not alone, send me an email and let me know how many other people you had with you at your computer. That helps me with attendance numbers because only one person can sign up, but more people can sit and watch. So if you can send that to me. And then if you want to go back and take a look at this presentation, take a screenshot of this. And if you want to go back and look at this presentation as well as the rest of our Weather 101 presentations are at the link that's at the bottom of the screen there. Bill, I got your extra person there, so thank you.